All right, hello everyone. My name is Ryan Nugent here at Cal Poly. I'd like to welcome you to our live Q&A panel on communications here for the workshop this year. We're very excited for this panel. We have some great panelists and talks that they pre-recorded. So please, if you haven't gone and checked those out, please check that out afterwards. And thank you for joining us. As you all know, this is a free conference this year in the virtual format, and we're only able to do that because of our sponsors. So for this session, we'd like to highlight one of our gold sponsors, one of our longest running sponsors, AAC Clyde Space. And we have a promotional video of theirs that we would like to show you. And then just as an FYI for everyone, the video does not have any sound, so nothing's broken. Again, I'd like to thank Clyde Space, AAC Clyde Space, for their gold sponsorship of this event. They've been a leader in the CubeSat community with their technology for almost 2 decades now. So please go visit their virtual exhibit. They will be available this afternoon. And thank you for all of the side meetings they've done in the mornings every day this week. With that, I'd like to introduce our moderator for this panel. Our moderator is Dr. John Bellardo. Dr. John Bellardo is one of the faculty and PIs in the Cal Poly CubeSat lab here. He received his PhD from the University of California in San Diego. He's been a professor at Cal Poly since 2005. Like I said, he's been a leader and PI in our lab for the last 12 years. So I'd like to turn things over to John.
All right. Thank you for the introduction, Ryan. I appreciate it. So today we're going to have 5 panelists on our communications panel. I'm going to go through and introduce each one and give them the opportunity to provide a brief recap of their pre-recorded presentation. And then while we're going through this, just as a reminder, feel free to use the Q&A tab on the bottom of the window to submit questions that we can ask the panelists after we go through the introductions. So I would like to start with Jose Velazco. Dr. Jose Vasque leads the Advanced RF and Optical Technologies group at the Jet Propulsion Laboratory, where he conducts advanced R&D of new RF and optical technologies and systems for telecommunications and radar for space exploration. Please provide us your short summary.
Great, thanks, John. So at the Jet Propulsion Laboratory, we have carried out development for what we call inter-spacecraft Omnidirectional Optical Communicator, in short, ISOC. So the ISOC is obviously a new optical terminal that was specifically developed to enable connectivity for CubeSats in constellations and in swarms. There are 3 objectives for this development. We wanted to achieve high data rates, gigabit per second data rates at the distance of interest. Also, we wanted to provide full sky coverage. So independent where the other spacecraft is located, we should be able to connect. And the third important goal for this development was to achieve multiple simultaneous links. So basically, this talk discusses our effort, 3-year effort, and then the development of this ISAC prototype.
Thank you. So if my memory serves, the ISAC prototype has 32 transmitters per
Yes.
ISAC, right? And with that, you're able to get full coverage. Well, probably not 360-degree coverage because you're going to be obscured. You know, something the spacecraft body is going to obscure something.
Yes.
But other than that, you can get full coverage.
Exactly. Yeah. So that's the idea. So each telescope covers about 0.4 steradians. So basically, yeah, you get 4 pi steradian coverage, except the body blockage that you discussed. And we are looking at options like deployers. What if we push the ISAC away from the spacecraft a little more? You still have blockage, but we could minimize that. And we are also looking at for longer distances, we are looking at ISAC developments or architectures with lesser amount of transceivers. So we're looking specifically at one case with 6 transceivers, and where each transceiver now has a little more coverage of the sky, but that will allow us to do longer distances. In this case, 4,000 kilometers.
Right. And so related to that, what is the current target distance for?
So we have 2 options. The one you described, the multiple faceted, like 32 facets, that is for swarms. So for swarms, we do like from 1 kilometer to maybe 500, maybe 800 kilometers. So that's one option for like a very kind of short, medium distances. For longer distances, we are looking at this dodecahedron design. And that the goal is to do 4,000 to 5,000 kilometers. So those are the 2 options we're looking right now. We're actually looking at a third option, a little more advanced, that it could do longer distances. We're looking at something to communicate from the moon down to Earth. So that requires a little more juice, more power, and a little larger apertures.
Yep. Thank you. Next, I'd like to introduce Ryan Kingsbury. Ryan Kingsbury is co-founder and CTO of Blue Cubed, a startup focused on low swap optical and RF communication solutions. Prior to starting Blue Cubed, Ryan worked on Planet's Dove satellites, and he also holds a PhD in small sat optical communication at MIT. Ryan, please.
Hi, John. Thank you for the introduction and for the invite to participate today. In my talk, I describe inter-satellite links, specifically optical inter-satellite links. And the goal of the talk was primarily to educate the audience on how small sat applications of optical inter-satellite links differ from the ones that are more widely published in the literature and that have been developed commercially. So specifically things like the Starlink and the Kuiper inter-satellite link systems. There's a lot of really important design differences when you're focused on a very low size, weight, and power implementation of an optical inter-satellite link. So I try to cover some of those design trades in the talk. And I also describe some of the product developments we're doing at Blue Cubed, specifically our Cobalt optical transceiver module, which is currently going through flight qualification.
Thank you. Yeah, so one of those trades you did discuss was the wavelength selection, right? And there are 2 wavelengths that you spent a lot of time looking at. I guess one question I had was, were there other wavelengths considered past those 2, or is the availability of components or some other reasons where those are just out of hand, not suitable?
Yeah, it's primarily driven by component availability. So there's a lot of work in the field to use fiber telecommunications components. Those are predominantly at 1550 nanometers. And there's been billions of dollars in research and development put into that industry. So it's very enticing to use those parts. And they can provide truly remarkable performance. I mean, 400 gigabits a second on a single wavelength for 20 watts, transceiver power is available commercially today. But unfortunately, with those wavelengths, there's a lot of other overhead that you have to deal with in a ISL sort of application, and particularly when power is at a premium, falling back to visible and near IR wavelengths is a very attractive alternative that's worth considering.
Sounds good. Thanks. Next, we're going to go over to Ashiqur Rahman. Ashiqur Rahman is a graduate student in mechanical engineering at the University of Texas, El Paso. He's working as a research associate at the Aerospace Center. Ashiqur, can you please provide a brief overview of your presentation?
Sure. Thanks, Dr. Velazco. So yes, I'm with the University of Texas at El Paso. We are developing a 3-unit cube satellite for the geostationary transport orbit. So we got the launch opportunity from the United Launch Alliance. We participated in their CubeCorp competition in 2016. We stood the first place. So as a prize, we will be launching our satellite to the GTO. So previously, we were planning to put a 1-unit satellite, a 1-unit CubeSat into the GTO, which have a conductive printing capability. So we were trying to demonstrate in space self-repair of an electrical system. So the damages that happens on the solar panel because of radiation, we were planning to repair those in space using our first satellite. So somehow the launch was delayed. The ULA launch was delayed. So we launched our first CubeSat into the low Earth orbit last year, and the mission was successful. So for the GTO mission, we are trying to develop a 3-unit cube satellite. So however, we are in the concept development phase at this moment. So we are setting up communication parameters. We are running simulations, then numerical calculations to figure out what kind of communication parameter we can use. So as per the preliminary simulation that we have, and we are still working on that. So it shows that for the apogee, we should be able to communicate using a 600 bps data rate. We are trying to use a 6-watt transmitter in conjunction with a 6 dB directional antenna. So with that, we are receiving 120 decibel milliwatt of received power at the receiver end, so which gives an impression that we should be able to reconstruct the signal. The reason we are setting up low data rate at the apogee is we would like to incur like low bit error rate at the ground end. So that is why we are reducing the bit rate from the apogee. However, at the perigee, we have a 1 Mbps. We are targeting for a 1 Mbps data rate. So we are trying to develop a radio, which should adjust the communication parameter based on the orbital positions. So we have other attitude sensing methods, star tracker, horizon sensor, and also as an actuator, we are planning to use electrical thrusters, microcat thrusters for the fine adjustment and to achieve the pointing accuracy. So also another mission challenge that we have found is the radiation danger because of the charged particles that are present in the space environment. So we are, as per the STK simulations, we are watching a 1000 rad of total ionizing dose in 6 months period. So we are assuming that 3 millimeter of titanium shielding should help us to address the challenges of radiation. So yeah, that's pretty much all about our mission summary.
Sounds good. The concept of changing your bit rate depending on your distance from your ground station is one that's been implemented successfully a number of times, which is good. But I guess the question I had is, I know as you get further away, obviously your bit rate goes down, right? And then you have this trade-off because you still have to operate your transmitter, and the transmitter is still consuming the same amount of power as it does when it's near the Earth, but you're getting a lot less data rate. So my question is, have you considered the impacts on the power budget of actually trying to operate the transmitter continuously the whole time? And is there a trade-off point where you have to lower the data rate so far to close the link that it doesn't make sense from a power standpoint and a data return standpoint to operate the transmitter?
Yeah, so we were also working on the power budgets. So the thing is, we don't have that much power for that we can integrate in a small satellite, right? Like the small satellite has constraint, like size constraint, power constraint. So obviously we cannot use 1 unit space in the satellite for where we can put down a big EPS. Obviously, we should have a restriction on the power. So given the power that we have available on the satellite, we are trying to use the same amount of power, but still we should be able to get we are trying to extract the best RF output power from the battery in terms of communication, like in terms of radio transmit power. So yes, we'll be using the same battery power that is available. And also there are other payloads in the satellite, so we have to secure the power for those payloads as well. And also we have to make sure that we are not discharging too much of the battery power. So given the power available for the COM, we would like to set up the communication parameters.
Okay, thank you. Next, we're going to go to Manolis Surligas. Manolis' background is computer science and telecommunications. He's an open source enthusiast and core contributor for the Libre Space Foundation since 2015, conducting research and development for SDR and DSP activities. He was also the leading engineer for the comms of the UpSat CubeSat and for the upcoming Waiting Inside the Rocket Fairing cubic 1-2 pocket cubes. Manolis, please, overview of your presentation.
Hi, everyone. Thanks for the introduction. I'm Manolis from Libre Space Foundation, a non-profit organization located in Greece. Since 2015, we have been involved with various space projects. One of them was the UpSat, was the first open hardware and open software CubeSat. And then we have the pocket cubes, the cubic missions, which are already inside the fairing of a Firefly rocket waiting to be launched into space. So perhaps the greatest project of Libre Space Foundation is the SatNOGS. And we had the presentation the first day of the workshop. So if you want, you can go and check it out, what SatNOGS is. In a nutshell, it's a network of ground stations using software-defined radios to decode and demodulate and decode data from various satellites. So this ground station network is crowdsourced from various amateur operators across the world, and every demodulated data uploaded into our infrastructure for further visualization through Grafana and different kind of dashboards. So we had the network, so we wanted more, and having all this background with previous missions of UpSat and Cubics, we had the chance to go for a bigger communication boards like the SatNOGS comms that I have presented, which is suitable for CubeSat missions for up to 600 kilometers, so LEO, and has two different interfaces, one for the UHF and one for the S-band. Everything, the schematics, the hardware, the software, and all the development process is open source and open hardware. And the entire development process can be found on our GitLab repositories. That are also links are also available on my presentation. So go and check it out. And if you have any additional questions, use the QA session, or you can find us on our Matrix channels on IRC. Thank
you. So I personally know a number of CubeSat operators who use and benefit from SatNOGs. It's a great, it's a great network that a lot of people both contribute to and benefit from both. So my question is, what additional benefit would using, let's say we were planning to use SatNOGs or rely primarily on SatNOGs for operating our spacecraft, and I was considering using the SatNOGs COM radio, right? What additional benefit do we get from using SatNOGs COM paired with the SatNOGs network versus using a different radio paired with? That's a nice question. Yeah. So you gain the 100% compatibility with the SatNOGs network already. So you get the comms and you have full compatibility with the existing network. You can use the entire network to schedule observations and fetch data from your satellite. And with this way, of course, you increase the availability of your satellite. Also, we provide the command and control interface. So you can use some of the ground stations around the world that are uplink capable and automatically schedule uplink sessions and communicate with your sat. So yeah, right now, 100% compatibility and increase of the availability of your sat with the SatNOGs comms CubeSat comms subsystem. Okay, thank you. I know one of the things that is always not concerning, but that I'm always thinking about, and hopefully other folks deploying CubeSats and building CubeSats are as well, is a licensing standpoint. So whenever I see uplinks coming from multiple countries, I might actually loop back to this question from a laser comm standpoint as well. But whenever I see uplinks coming from multiple countries, I get worried that somebody's going to have to go through and get a transmission license for each country in order to use that station. Do you have any insight as to how SatNOGS helps to address that, or is that still sort of a work in progress?
This is a work in progress, and we are fighting for this, and we are trying to find a balance between these legal issues, let's say. So for now, the uplink stations belong to amateur operators that are licensed to operate on these frequencies, and you have to talk to your host light as you use another amateur operator to send uplink commands to your sat. So this is not it's not the best case, but it's the legal, let's say, aspect of how to use the network right now. But we have several actions towards this. Okay,
sounds good. Thanks. Next, we're going to hear from David Hansen. David Hansen is a Cal Poly SLO graduate, so an alumni from the institution here hosting the developers workshop, graduate in physics, director of the radiation effects and hardening at Space Micro in San Diego. During his 20+ year career, his research has covered the degradation of semiconductors due to the natural and man-made radiation environment in space. David, please provide us with an overview of your talk.
Thanks, John. One thing I do want to mention before I get too much into that is that we're hiring at Space Micro. So if there's any students who are going to be done soon and are looking for something to do after graduation, you can either check our link or contact me directly. And one of the things, when we look at my talk sort of in the overview, I guess the thing that stood out to me first was that Ashiqur has really a fantastic zoom background, the northern lights. Those are caused when you get solar particles that are impacting the atmosphere and the Earth, and that causes that beautiful glow. That glow in the atmosphere, you can imagine that sort of thing is going to do horrible stuff to your electronics. And that's sort of where my talk starts. Space is a difficult place to do business. And in order to deal with that, you have to have, if you want to do that in a really reliable way, you have to have electronics that are going to be able to handle the radiation environment. But those aren't always cheap. So you have to make some choices between the reliability of your parts and how many errors, how many outages you're willing to deal with. That often comes with a price, either monetarily or availability. And so my talk goes into a lot of the detail in terms of the trades that you have to make that. But I also then discussed our CubeSat space processor, and that's a product that we have here at Space Micro, and use that as kind of just a test case for how these trades would look. You can use rad hard parts, and it ends up costing you maybe 10 times per part at least. Or you can use the rad soft parts. And then, of course, what you would really need is going to depend a lot on where you're flying. The space environment varies depending on your altitude and where you are in relation to the radiation belts. And that's kind of my talk in just a nutshell.
Thanks. One of the things that I noticed that I've seen this approach being employed in some other hardware is where you just harden a part of the spacecraft, right? And in this case, I believe you're talking about hardening the watchdog in particular, where that's responsible for protecting other components or rebooting other components of the spacecraft. So there's basically a design trade-off or a cost trade-off, so that you can use the cheaper rad soft components and use the rad hard watchdog to help protect them. So I guess my question is, how far can that scale, right? Both in terms of the total number of components the rad hard watchdog could protect in the whole spacecraft, and how few rad hard components you need to build the watchdog, right? So how far can you push that lever in both directions?
Well, it's not a simple answer, right? Because you can essentially make a watchdog for your entire satellite, just flip the whole thing on and flip it off. You'd have this small percentage of the circuitry that would have to be rad hard. And, in that sense, it's just a matter of how much you're willing to pay for that particular thing and how much of the satellite you need to cycle. But part of the issue there as well is that you don't necessarily need a whole satellite to be rad hard. So a lot of those systems, if you get a glitch on them or two, like on some of your power systems, maybe you've got enough capacitance and you're done. That transient will just go off into, you can drive it to ground using a filter or something very simple. So I think part of what I was really sort of driving at is the scalability, the size, how much you want to protect is really just kind of a function of how much you're willing to pay for it, and then how sensitive your parts are, and then how bad the environment is going to be. Those are sort of the three things that come into that mix. But you can really scale that approach up as high as you want.
Sounds good. Thank you. Okay, so we've got a couple of questions that come in. I know that we've had some text answers, but I wanted to give our panelists the opportunity to respond verbally as well. So first we'll go to Ashiqur. They're asking about the OF4 mission. Could you give us insight into the assumption model behind the link budget?
Yeah, sure. Right, sure. Thanks for your question. So our idea is to use lower bit rates at the apogee so that we can encounter less bit error rate at the ground end, using the power that is available in the satellite. So we're not increasing the transmit power because we have restrictions on that, right? We cannot go beyond 6 watt, let's say. But also we have capabilities of, in terms of capabilities of antenna, we cannot go beyond like 6 dB. So using those parameters, we are getting a negative 120 dBm with decibel milliwatt of received power at the ground end. So with that communication parameters, if we are watching that, if we can lower down the bit rates from the apogee, we're having a less bit error rate. But that is adjustable. When the satellite is coming closer to the Earth, it's near to the perigee, then it will automatically increase the bit rate, and we are assuming to have a 1 Mbps at the perigee. So that's the idea. We are at the very beginning, like the concept development phase at this moment. So we would love to have any suggestions as well, like if you have any.
Sounds good, thank you. We have another question that was addressed to everyone on the panel. Are you considering the possibility of using multi-hop relay for non-LEO missions? I know Jose answered that briefly with an affirmative. I don't know if you want to add to that or if other folks on the panel would like to address the question as well.
Very quickly, yeah, I could add to that. Yeah, so over the past year and so, I've been looking at that option of developing what I call an interplanetary network. And so that we use relays of not only small sats, but swarms of small sats. And each swarm would be actually interconnected optically. So it becomes like a synthetic aperture. And then you could have these synthetic apertures distances of astronomical units, basically, and you can communicate at high data rates. So I did a study, I got funding within JPL, and yeah, I'm finalizing the report right now. I'm trying to get it out to share with the community. So I'm just trying to get the permissions, but I'll share that information. Yeah, definitely, especially I think based on swap size within power, I think optical is, and this has an advantage there over RF, but I was looking mostly at optical interconnectivity along the solar system.
Thank you. Would somebody else like to address that question as well? Contemplating the possibility of using multi-hop relay for non-LEO missions. Okay. Sounds good. So one of the, again, I'm going to bring the licensing back up, right? I know via some of the work we've done with laser comms that when you're communicating with Earth, you have to worry about going through the laser clearinghouse and whatnot to make sure that there's your safety is taken care of, right? And I've also got the sense that maybe with its space to space, obviously it's a bit different, and maybe our licensing regime hasn't quite caught up with that communication paradigm yet. So I'd like to get your thoughts about sort of the current state of that licensing, and if you think it's stable in its current state, or if it's going to evolve as the various regulatory agencies realize that it's being widely deployed. So do you have any?
I can take a stab at that.
Yeah.
So on the licensing front for laser comm, the two main issues people tend to worry about are the the eye safety and pilot distraction hazards that you mentioned. Those are, of course, relevant for space-to-Earth links, particularly systems that have an uplink beacon that is used to help with the alignment process. And then separate from that are the laser clearinghouse requirements. I believe those are only pertinent for U.S. government organizations or organizations that receive their funding through those sources. Internationally, I don't believe there are any concrete licensing requirements out there. My personal opinion on it is that I think it's unlikely that it will ever be regulated to the same extent that RF systems are regulated. And that's primarily just based on the physics of it. These systems have very narrow beam widths. It's not quite the same concept of a shared medium as radio spectrum is. So I'm optimistic that it will remain to be a very friendly environment in terms of regulation.
Sounds good. Thanks.
Yeah, I can just add to that. Yeah, we JPL also we're working on another optical communications project. We call it Deployable Optical Receive Aperture, DORA. And so in DORA, we are looking at actually a LEO mission right after this development. And so we're looking at those exactly the same concerns. Okay, we need a ground station. What are the limitations? Definitely pilot distraction is an issue, but that's typically an issue with visible lasers. Basically you don't want to distract a pilot that's landing spacecraft and that sort. But for IR, invisible laser, I guess 1550 nanometers is considered non-ionizing, even though I don't agree with that. But I think that's the tendency is to go to 1550, and that's what I think NASA itself has decided that 1550 is safe for astronauts. So there's that other extreme. But yeah, going back to that, for IR, the only limitation I think is your ground station nearby. You have to there's a power density limit or a radiance limit, maybe a few tens of feet away from the transmitter, just to actually damage your eye, just because of the power density more than anything else. So I think those are two concerns, but I agree with Ryan that I think it still is an open, it's going to be laser, is a bandwidth, open bandwidth of frequency that it would be, if it is regulated, it would be maybe in decades from now. And there are people looking at the next generation of connectivity in like a 4G, 5G optical generation, which would be all optical. And maybe in those cases, you have optical beams all over you. So maybe then you will have more regulation.
Yeah. Okay, we had another question come in regarding the, excuse me, the optical comms as well. So do optical pointing requirements preclude certain mission concepts like continuous Earth imaging?
I wouldn't say that it precludes those missions. I mean, it certainly would imply that your spacecraft design needs to have some sort of pointing mechanism for the either the optical comm system or the imager, so that you can track both of your pointing targets at the same time, one being the Earth, the other being the other end of the link. So yeah, there's certainly complexities that arise from that, but certainly it doesn't preclude those use cases.
Yeah, I think I will have to mention that. Yeah, that's if you look at my paper, we developed this omnidirectional optical communicator. It's quasi omnidirectional, but we call it omnidirectional. So that was the purpose too, that you could have omnidirectional beam, optical beam, so you could communicate in all directions. You could collect data, and then at the same time you could downlink your data very quickly to your ground station, to your optical ground station. So there are ways people are beginning to work on that now, more putting together multiple optical terminals, so you have full sky coverage. And so I think that's gonna get easier in time, also with this new technology called integrated photonics. Integrated photonics allows you to integrate optical components into a chip. So we talk about size, weight, and power. I think that's the name of the game for CubeSats. And so with integrated photonics, you're gonna minimize swap, size, weight, and power, and that's gonna allow you to have more enabling optical systems.
And so when I think of something like ISOC, which you were presenting, what that was designed for space to space. What's your main limiting factor of taking that same design and scaling it to do space to Earth instead?
Yeah, no, we're actually looking at that specifically. I think this there is no limit. Depends on the distances, obviously, but yeah, we are actually looking now with a partner. We are looking at creating constellations, really a constellation of about 60 spacecraft around Earth, and would be for connectivity as well. And the idea would be to do crosslink and downlink to the ground, all optical. So there's no limit really. Obviously, the atmospheric attenuation and issues that provides that add a little bit, you know, to your link budget calculation, but otherwise, it is very doable. The only thing you have, the only issue that is clear with optical is clouds. You know, if you have clouds, then your weather could be a problem. But you solve that with cross-linking in enough ground stations. You know, yeah, because you can cross-link to until you find a spacecraft that has line of sight with a ground station. So we are looking, actually actively looking at that. But once I think that's the goal, you want to have anyways. If you want to do Earth global coverage, you need to have ground stations across the whole. I mean, at least a large number of ground stations, and then you have a large number of spacecraft in your constellation. Then using crosslink, you can solve the issue of clouds, basically.
Okay. Thank you. We had a question come in for Manolis. So will SatNOGs provide a unified platform for transmission from different ground stations, similar to how it's the uniform platform for receiving, or are there security concerns? And I can add to that, maybe additional concerns besides security that would prevent that.
Yeah. So this system is under development right now, and the security concerns are. We have dealt with the security concerns as far the transport layer concerns with the CCSDS SLE provider. So, and this is expected to be integrated into the existing SatNOGS network. Regarding the legal issues, if another ground station that is located in a different country is allowed to transmit, there are several discussions around that. But maybe some ground stations from some amateur operators are allowed to transmit in certain frequency bands. So yes, you could use that in the same manner you use the existing ground stations to fetch data in order to transmit them.
That sounds good. Thank you. Okay, so I want to say at least 3 of the presentations that talked about you know, a product in various stages of development that somebody might want to consider to integrate to their CubeSat as part of their mission. So I'd just like to go around quickly and figure out sort of what stage of development. Is it something that's available now? Is it something you might be able to you know, baseline 2 years down the road, or what the what the state is for all 3? And I'd like to start with David, please.
Yeah, we're ready now. We have parts in house, and we're ready to take orders if you want them.
Sounds good, Ryan.
So we are going through environmental qual with our transceiver product today, and we're hoping to get it on orbit for an initial orbit demo as soon as possible, hopefully in the next 12 to 18 months. Okay. And I will add that we're actively looking for partners or anyone who's interested in the technology.
Okay. And Isaiah, there are plans to commercialize or transfer the ISOC technology?
Yes. Yeah, actually, I can, yes, maybe without getting in trouble, I think I can say that, yes, it's been licensed. And actually, the ISOC is, we plan to fly a version of the ISOC early next year. It was this December, but it's been pushed to a couple of months later. And then after that, we plan to fly it almost every three months. There are different missions that we plan to. So we are beginning to deploy it. And so that's going to take the TR level, you know, from 4, 5 to 7, 8. You know, it depends. We're going to do. So next year we'll fly it several times in different missions. And then the goal is to make it available to the community too. Once we elevate the TR level, And once we have these multiple versions, you want for swarm, we have this version, you want more longer distances, this version. So yeah, but it is coming. So if you are interested, guys, let me know. But yeah, we would like to put into all multiple missions as possible, as many missions as possible, and help you, use it in the proper way.
Sounds good. Manolis, what's the readiness state for the SatNOGS comms solution?
Okay, so right now we are doing experiments with the RF front end, checking especially the AGC, the automatic gain control, and the next phase is to evaluate also the IQ interface. We have the SatNOGS comms can operate in an IQ mode, like an SDR, for example, using the onboard Zinc FPGA. With that done, we expect that we will be able to release it at the end of this year. And of course, this is not this is never a non-ending project. It is open source, so yeah, contributions will be done afterwards and improve the product and become. And even operators or users can come back, check if we have the bugs or whatever, because everyone have bugs on their products, right? And correct them and make a better product for the next one. So this is open source, right?
Yeah, sounds good. Thanks. It looks like we're getting close to running out of time, so I'd like to go through and see if folks have some closing statements, remarks they'd like to make before we sign off here. So I'd like to start with Ashiqur. Do you have some closing remarks?
Yeah, sure. I'd like to thank you. I'd like to thank the CubeSat developers team for letting us present our work. So we are at the very beginning stage. We're at the very earliest stage. We are still planning our mission. So in the next couple of years, we will have several design reviews with our industry partners, and we will also be planning to incorporate other scientific experiments into the satellite. So it is one of the mission objective is to demonstrate the S-band communication capability from the apogee, but at the same time, we will have other scientific experiment as well. So in my video presentation, there's my email has been mentioned in there. If you have any suggestions that we can implement or any other payloads that that you think should be exciting to incorporate in the 3U CubeSat for the GTO mission, please feel free to send us an email. And any suggestions would be really helpful. Thank you.
Thank you. Let's go to Ryan. Do you have closing remarks?
Yeah, John, well, I'd first of all just like to thank you and the rest of the CDW team for putting on the event. It's great to be back at the conference, albeit virtually this year. No, I would just like to say, in terms of our product development progress at Blue Cubed, if any of the folks in the audience have a need for inter-satellite or even downlink optical comm systems, please reach out to the team. We also have an X-band transmitter product that is flying this year on two university CubeSats. That's available to ship pretty much imminently. So yeah, if there's any interest, we'd appreciate the contacts. And if there are students that are interested in engaging with the team, they shouldn't be bashful. They should reach out as well. So thanks again for the opportunity.
Yep. Thank you. Dave.
Well, I'd like to thank you also for just the opportunity to talk here. I think that it's really kind of an exciting time to be in space. It's an exciting time with all of these different missions that are going up, and sort of the fact that it's gotten cheaper means that there's a lot more innovation going on. It's a little bit analogous to what's happening with the App Store, right? A whole lot of new innovation going on in space now. I would just say that if you have any questions about my talk, feel free to contact me. Again, radiation tends to be something that's less critical with CubeSats because the missions tend to be short, but it's still something I think that can be pretty easily integrated into whatever types of architectures you might be developing. So thank you.
Sounds good. Thanks. Jose.
Anyways, I just wanted to reinforce what David was saying. These are very exciting times. I think everybody in the audience, this aerospace industry, the space industry is booming. You know, I did some research. The space market is going to reach the $1 trillion mark, I think, next year. So it is we're in the right place. I think small sats are fantastic. I'm personally biased, I guess, towards small sats, but I think they can replicate what larger counterparts can do. We can do it better. You have additional benefits of doing small sats. So by developing this optical communicator, that's what we wanted to do. Is we wanted to help small sats to reach the next level, and that is developing swarms and constellations. But the future is very bright. So just contact me if you have any questions. But I think this conference is key, and I thank you for John and everybody in the team, CDW team, for inviting us to present.
Sounds great. Thank you. Manolis.
So thank you for the organization and the hospitality. And I would like to say to any future CubeSat mission team that if they want to use our comms board, it will be fun because they will be also be involved with an open source and open hardware project. They will have the chance to alter it and in order to fit their needs, and also help back the community. So if you like more info, please join our IRC channels and have a talk with us. So again, thank you.
Sounds good. Yes, I'd also like to express my sincere thanks to everyone for taking the time to have this conversation today, taking the time to put together your pre-recorded presentations on all the interesting work. And hopefully we will be able to meet in person next year and have these discussions face-to-face instead of all virtual. So with that, thank you, and I'll pass the baton back to Ryan to close us out.
Thank you very much, John. I think you did a great job of pretty much closing us out. I'd like to also extend a special thanks to all of our panelists for that great discussion and for all of recording those presentations for us as well to share with everyone. I hope we can host you all next year at Cal Poly in person and get updates on the progress of all of your work. And again, thank you so much, and look forward to watching your progress in the future. With that, we will close out this session. So everyone, please join our next session, which will start in about 10 minutes. Thank you very much.